Objective 4, 2.8, higher derivatives. If f is a differentiable function, then its derivative, f prime, is also a function. So it's the function that gives the slope of the tangent for f at any point x, at any x coordinate. So f prime may have a derivative of its own denoted by f prime prime, f double prime. This new function, f double prime, is called the second derivative of f because it is the derivative of the derivative of f. So a second order derivative is called a second derivative. Using Leibniz notation, we write the second derivative of y equals f of x as, okay? So derivative with respect to x, derivative with respect to x of what? Well, it's the derivative with respect to x of the derivative of y with respect to x. And so the Leibniz notation for the second derivative is d, and then you've got 2, because it's the second derivative of y with respect to x, and here the 2 is on the outside. We aren't thinking of dx as having a meaning apart from the rest of the symbol, the entire symbol. But that is the way in which we will have to write the second derivative. Second derivative it's an easy idea, and computationally it's easy also. The second derivative is the derivative of the derivative. Example. Here's a function f of x equals x cubed minus x. Find and interpret f double prime of x. Okay. Now, we're not going to take the time to use the definition of the derivative and apply it to f. So we're not going to take the time to say, okay, let's get the limit as h goes to 0 of f of x plus h minus f of x all over h, and apply that to f of x. We will do that. We will apply that to f prime. Okay, so we're just saying, for the sake of time, let's just say that f prime of x is 3x squared minus 1. And so let's apply the definition to that function, because the derivative of a function is a function. Second derivative, at least in this case, the second derivative is f double prime of x equals f prime prime of x. So we're going to take f prime of x, which is this, and differentiate it. And that means taking the limit as h goes to 0 of the function evaluated at x plus h minus the function, which is the derivative, evaluated at x all over h. Well, that function is 3x squared plus 1, right? And so f prime of anything is 3 times the square of that thing, 3 times the square of that thing minus 1, and that thing will have to be x plus h. So 3 times the square of that minus 1, and then minus f prime of x again all over h. Well, at this point, it's pretty straightforward work. Okay, so doing the squaring and distributing the 3, we have 3 times the perfect square trinomial, x squared plus 2xh plus h squared, right? That's what we had up here. X squared plus 2xh plus h squared. Okay. And then the minus 1, right? Because we had 3 times the square of x plus h, which is the same thing as this, which is the same thing as this trinomial here. And then we had the minus 1, and then we're subtracting f of x, which means subtracting each of the terms of f of x. I'm sorry, f prime of x. Okay, so let's remember what f prime of x is. F prime of x is 3x squared minus 1. Okay. And so we're going to have the normal work that we normally have. The regular cancellation will take place. That takes place when we're dealing with polynomial functions. And all of the remaining terms have a factor of h. Right? So that's the limit. As h goes to 0, h 6x plus 3h all over h, and we're canceling those h's. Well, as h goes to 0, 3h goes to 0, but 6x is just 6x. And that's what we get for the second derivative. Okay, so there it is. There is f double prime of x, the derivative of f of x. Interpretation. Here are the graphs. You see f, that's the blue one. And then this pink one, 3x squared minus 1, that's this one. Okay, that's the pink one. And then 6x, that looks like it's green. Okay, f double prime. Okay, so slope of the tangent line of the blue graph is what we have in the pink graph. What about f double prime as an interpretation? We can interpret f double prime as the slope of the curve y equals f prime of x at the point x f prime of x. So we could take the tangent lines of the pink graph, okay? So slope of the tangent, slope of the tangent, slope of the tangent, slope of the tangent, slope of the tangent. So do to the pink graph what we did for the blue graph, and that would give us an interpretation of the green graph, the graph of the second derivative. In other words, it is the rate of change of the slope of the original curve y equals f of x. Of course, if we're talking about the rate of change of a slope, the slope is a rate of change. So we're really talking about a rate of change of a rate of change. Notice from figure 10 that f double prime of x is negative when y equals f prime of x has a negative slope, and positive when y equals f prime of x has a positive slope. Okay, when this is going uphill, you know, at this point there's a tangent. When it's going uphill, well, for that value of x, the green, you know, that's positive. Now that's out of the window, but the green graph has positive y coordinate. So the graphs serve as a check on our calculations. We could also talk about concavity as well as a way to interpret second derivative. to the left, the blue graph is concave down, and the green graph has negative values over there on the left. On the right, the blue graph is concave up, and the green graph has positive values on the right. In general, we can interpret a second derivative as a rate of change of a rate of change. A derivative of a derivative. The slope of the tangent line of the slope of the tangent line. Those familiar example, the most familiar example of this is acceleration. Okay, so we've been talking about the geometric interpretation. What about the one having to do with velocity? Okay, acceleration, what is that? S equals S of t. So we've got a position function s of an object that moves in a straight line. We know that its first derivative represents the velocity v of t of the function of the object as a function of time, right? Velocity is the derivative of position. Okay, well, velocity is the derivative of position, but now we're going to talk about the derivative of the derivative of position. That is the derivative of velocity. Well, that's acceleration. The instantaneous rate of change of velocity with respect to time is called the acceleration a of t of the object. Thus, the acceleration function is the derivative of the velocity function, and is therefore the second derivative of the position function. And so this is extremely useful because we all have experience with velocity and with acceleration. You know, even if you're a high school student and you don't even drive yet, you have been in cars, and you've been in cars that have had certain velocities and cars that have accelerated and decelerated. So acceleration is the derivative of velocity, which is the derivative. Acceleration is the derivative of velocity. Velocity is the derivative of position, making acceleration the second derivative of position. In Leibniz notation, we've got this, okay? Acceleration is the derivative of the velocity function with respect to time, and that's the second derivative of the position function with respect to time. Okay, third derivative. Okay, what about that? We're starting to get out of the range in which our intuitions can help us understand this, and it begins to become more abstract, but that's okay. It doesn't make the math a lot harder. The third derivative, f triple prime, is the derivative of the second derivative. Okay, so f triple prime is f double prime prime. So f triple prime of x can be interpreted as the slope of the curve y equals f double prime of x, which is the green one, which actually was the same the whole way, right? Because it was a line. Okay, so the slope of a line is the same no matter where on the line you are. Okay, if you remember that green line. Okay, well, the slope is constant. So that if we were going to have a graph of that, must be a horizontal line for the graph of f triple prime. Right? We had a graph of the green line that looks something like that. Okay, y equals f double prime of x. Okay, well, triple prime, that graph would just be a horizontal line because the slope of the tangent to the graph of y equals f double prime of x, that's the same all the way across. So the graph of the third derivative would be a horizontal line. If y equals f of x, then alternative notations for the third derivative are just exactly what you'd expect. Y triple prime, f triple prime of x, which we've seen. The derivative with respect to x of the function, which is the second derivative of y with respect to x. And so in Leibniz notation, it looks like d cubed y over dx cubed. Okay, what about beyond that? We can also interpret the third derivative, okay, not beyond that. We're still talking about third derivative. Third derivative physically in the case where the function is the position function s of an object that moves along a straight line. S triple prime is the derivative of s double prime, which is the derivative of acceleration. Okay, now think about that. What would that be like? You've got position, okay, car's in a position. Then you've got velocity, okay, that's the, to oversimplify, that's the speed of the car. And then you've got the acceleration of the car. Maybe it's getting faster and faster and faster, or maybe it's getting slower and slower and slower. But then what's the rate of change of acceleration? Okay, the third derivative of the position function is the derivative of the acceleration function, is called the jerk. So jerk is the derivative of acceleration with respect to time, which is the third derivative of the position function with respect to time. And yes, many of us have gone through the phase of calling certain people we know third derivatives. Thus, the jerk J is the rate of change of acceleration. It is aptly named. Okay, so now here, we can get some sense from our experience of what we might, how a way to understand the jerk or third derivative of position function. Jerk J is aptly named because a large jerk means a sudden change in acceleration. Okay, you're accelerating, but then there's a change in that. Maybe you hit an object. It causes an abrupt movement in a vehicle. The differentiation process can be continued. We could talk about fourth derivative, f quadruple prime. It's usually denoted by f, and then it looks like an exponent of 4, but it's in parentheses. So with those parentheses around an exponent, you're talking about a derivative, the nth derivative, whatever it is. In general, the nth derivative of f is denoted by f, and it looks like an exponent, whatever n is, that's in parentheses, and is obtained from f by differentiating n times. So if y equals f of x, then we write y a raised n in parentheses, or f with a raised n in parentheses of x, or dny over dxn. Okay, Leibniz notation. Of course, we are not thinking of this as a ratio yet.